So good morning, and it's nice to see so many people at this early hour. So welcome everyone. I'm incredibly happy to be speaking with you. My name is Piotr Zentemski, and I have been developing drones for quite a while now. I'm one of the Paparazzi UAV system developers. I actively contribute software and hardware designs to the project, help maintain the website and the server infrastructure. So I might be a little bit biased, but I will try to be as objective as I can. My company, 1BitSquared, performs open source micro UAV consulting, development, and manufacturing. I have been working in that field of autonomous unmanned aerial vehicles for almost 7 years now. And I'm also the developer of LISA M and LISA S autopilots that are part of the Paparazzi platform. When we read about drones in the news, we perceive them as big, scary, expensive, and very likely lethal. But this is not what we will be talking about today. We will be talking about the small, the affordable, the sometimes odd, and sometimes also quite big. I'm also only interested in drones that adhere to the same ideal of freedom as freedom of speech. And some of those that everyone could build if they had a minute to spare. I know this is quite a problem for many of us. Also, I think a drone needs to be able to fly by itself. At the most simple level, the only thing that one has to tell the aircraft is where to go and what route it should take to get there. These flight instructions can be greatly more sophisticated than that. Now that we have set up some borders for the things that we will be talking about, let's start with some history. I'm pretty sure there are projects that are older than what I could find, but this is as far back as I could uncover. The project is simply called Autopilot, or it has some DIY thing in it too, and can still be found on SourceForge. The project was created in 2001, and it's still being worked on. That's the funny part. The Autopilot has an open source stabilization and navigation system for helicopters. They documented their first fully hands-off of the remote control flights in June 2003. The next project was the development of Paparazzi UAV. I know what you might think. Paparazzi is a strange name, but I just attribute it to the French humor. Around the time when the previously mentioned Autopilot project was performing their first autonomous flights, Pascal Brisset and Antoine Durand from ENAC, l'École Nationale de l'Aviation Civile, in Toulouse, in France, decided to compete in the NCCA Super Aero autonomous flight competition. The original design used an off-the-shelf commercial FMA Copilot stabilization system, which was mounted on their twin-jet remote-controlled airplane. They were feeding control signals to it from a laptop on the ground that in turn was running the actual control instead of a human pilot. This can be a rather unreliable setup. It is difficult to predict what the black box commercial hardware and software will do, and how it will react to the computer-generated commands. This resulted in unavoidable oscillations and crashes. Antoine and Pascal developed a board very similar to the one created for the Autopilot project, and reusing some of their remote control parsing code and algorithms, and also adding good deal of their own code, they were able to win the competition with that system. This inspired them to continue working on that project, and because they wished to share their ideas and collaborate with other enthusiasts, they released the software and hardware designs to the public, all under GPL. In the years that followed, more teams used Paparazzi system to compete in competitions and win a lot of prizes, involving fixed-wing aircraft and autonomous flight. Around the same time when Paparazzi was started, two smart German high school students developed a rarely before seen flying object for Jugend forscht. Jugend forscht is a national science competition for high school students which recognizes and rewards inventions and innovations. You might recognize the device they invented since it's quite ubiquitous by now, definitely here. Based on their invention, the company Silverlit started producing a quadrocopter toy called XUFO. I'm departing here from the open source premise, but stay with me because the innovation is an important one. As you might know, a quadrocopter is inherently unstable. That means it will fall out of the sky just like that if you don't feed signals to the motors. The rule of thumb is that it needs at least 100 Hertz updates to the motors so that it stays afloat. A human is only able to deliver at most 10 updates per second, if they are really well trained. Thus, the platform needs some kind of a mechanical or electronic stabilization system to make it flyable by a human. The XUFO was price optimized as a toy. It used a mechanical gyroscope with Hall sensor pickups. This is quite a mind-blowing considering it was cheaper to build and manufacture such a device than it was to purchase an off-the-shelf piezoelectric or micromechanical sensor. The mechanical gyroscope had many issues. It suffered from progression and as well as limited error angle before it started hitting the bracket, resulting in the so-called flip of death. These shortcomings and the fact that the rest of the XUFO electronics were quite simple created quite a big community of people that were modifying and improving the electronics and sensors for the platform. The exciting development and knowledge exchange that was happening at the XUFO forum was mostly German-speaking, but the forum provided a great meeting place for all the UAV community at that time. Sadly, the forum was disabled without a warning earlier this year, but there are efforts to get it back online. Most of the modifications that were based on the use of two piezoelectric gyroscopes and a lot of hot glue. But even though these modified versions did not look pretty, they flew better than the original, since they did not suffer from progression or the flip of death. Nonetheless, the sensors were difficult to get in single units. The piezoelectric sensors suffered from temperature drift, and mounting them perfectly perpendicular to the airframe was quite a trick. Thanks to those two sensors, it was possible to stabilize the most unstable two axes, namely if you say the front is here, the pitch, and the roll axis. So these are the two that this would stabilize. This is when the inventors of the platform, Daniel Gurdon and Klaus-Michael Dott, came back into the picture. Together with two of their college friends, Jan Stumpf and Michael Achtellik, they founded Ascending Technologies. They produced their X3D piezo gyroscope board that was a drop-in replacement for the mechanical gyroscope that was quite an improvement. The X3D board added one more axis of measurement, making yaw, so the vertical rotation, all stabilized too. While it was a commercial product, the development inspired a few other people to work on their own incarnations of quadrocopter electronics and solutions. Among them was Microcopter. Microcopter was mentioned in their, for the first time in an XUFO forum post in October 2006. Many of you might know of them already. They provided access to their source code and had quite a well-documented circuitry. This was great even though they were not technically licensed as open source, but something completely proprietary with very questionable status. The microcopter control board came with 7 degrees of measurement, adding a 3-axis accelerometer, so a linear motion in all 3 axes, that measured the Earth's gravitational acceleration, providing the absolute down vector. This allowed for the platform to stay horizontal with a smaller amount of drift. This feature allowed one to release the remote control sticks a bit before the quadrocopter drifted into something horizontally. It also came with a barometer, providing an absolute altitude information and making it possible for the vehicle to remain at a set altitude by itself. Another platform that I would like to mention was the Wolfferle board, also known as the Unmanned Aerial Video Platform, UAVP project. As far as I know, it was open since it was possible to access the source code. I am not precisely sure about the exact history of the project and whether it was actually inspired by the XUFO, but at the time during which they were developed are very close. The platform used more sophisticated macromechanical sensors. This made it quite a bit more expensive, but it also it was much more stable in flight. This stability made it much better as a video camera platform. Out of that particular project, UAVP-NG emerged, composed of a new group of people and its own separate philosophy. This new group mainly targeted quadrocopters, high-quality sensors, and it was meant for those who wanted to assemble the electronics themselves. They regularly released a stable source code under open source licenses, and as far as I can tell, their goal was a very high level of software stability and best sensors available on the market, and an advanced feature set. But since Amir, the creator of this project, is likely sitting here in the audience, he can tell you the details of that history better himself. They have an assembly here, so you should go and visit them. I bet they will be very happy to answer all of your questions. In the midst of all that development, a 3-axis magnetometer was added, resulting in 10 degrees of measurement and absolute information about the heading of the aircraft. The addition to the platforms that I already mentioned, there were many more other platforms too, TT-Copter, Armocopter, ArduPilot, with varying levels of openness and availability of the hardware. Most of the project originated here in Germany, and it took quite a while before it finally caught on in the US. For example, Jordi Munoz started working on his own IMU for Arduino that later became the ArduPilot around January 2008. This, over time, resulted in thriving commercial companies like 3D Robotics. As most of the solutions already contained a controller of some kind and a lot of sensors, it was an obvious next step to add a GPS and start teaching quadrocopters to fly by themselves. So this development was happening from both directions. The autonomy-focused, competition and research-driven projects like Paparazzi from one side and hobby multicopter-driven projects from the other. The Paparazzi group developed its own controller board dedicated to quadrocopters called Booz. Together with its algorithmic flight plans and flexible ground station software originally developed for fixed-wing airplanes, it started to morph into an airborne robotics framework rather than a pure airplane autopilot. Paparazzi was adopted by many universities as well as a bunch of commercial companies. The universities and companies helped to improve the platform and add features for the benefit of everyone involved. Thanks to the people involved, we are able to push the boundaries of what we can do with civilian drones every day. Other projects that came from the quadrocopter and hobby side of things started adding position hold and then waypoint flight plans to their existing stabilization hardware and software. So where are we now? Almost all open source autopilot systems of today, like ArduPilot, OpenPilot, and Paparazzi, Support fixed-wing airplanes in many configurations, a single engine, twin engine, flaps, ailerons, elevators, flaperons, elevons, and so on. Multicopters, not only quadrocopters, by a laundry list of different configurations, similar to airplanes, but even more so, 3, 4, 8, 12 motors in X plus over and under configurations. It is quite overwhelming how many possibilities this approach provides. Basically, attach a few motors with propellers to a bunch of struts, and you will probably be able to make it fly. Helicopters started the whole open source controller story, but to be honest, since the dawn of the multicopters, they do not seem to be the most common choice for conversion into a drone. The main reason is the cost of operation. The helicopter has a lot of very intricate mechanical parts that are expensive to manufacture. And if your software screws up and you crash, the fun becomes quite expensive very quickly. They are still being used in situations where you need a long flight time. It is easier to put together a turbine or combustion engine-driven helicopter than a multicopter. Recently, though, very cheap, very small helicopters have become available from China, making the helicopter an interesting platform again. More on that later. A new category of vehicles called transitioning vehicles is emerging. This is a combination between a fixed-wing aircraft and a multirotor. Transitioning vehicles take off vertically, can hover, and on a flip of a switch, or a software command can transition into a forward flight, making it quite more efficient. This can be also achieved by tilting the engines themselves and not the whole vehicle. As far as I know, Paparazzi is the only platform so far that supports this new aircraft class in the vanilla codebase, including autonomous flight. But other projects seem to be catching up slowly. Many projects used Atmel or PIC microcontrollers, 8-bit architecture and 16 MHz clock, or even worse, Arduino. But now, most of the projects are using ARM 32-bit processors that provide enough processing power to do some fun stuff without the programmers having to be code extortionists. This enables us to think about adding real-time OS for managing processes, for example, and encryption to the telemetry links, run more sophisticated estimation for more accurate control, or run intelligent path planning algorithms. The sensors have come quite a long way as well. For the last few years, thanks to the ongoing development of cell phone technology, the prices of micromechanical sensors have dropped significantly so that they have become affordable. They might not be the greatest, but they are good enough for most applications. And instead of paying $30 per degree of measurement, we pay $6 for 6 degrees of measurement, or $13 for 9 degrees of measurement in a single chip. Even though there are many different boards, at the core they have converged quite a bit. What they differ in most is the size and what integrated features they have, like radio communications, video overlay circuitry, servo connections, and communication channels to sensors and actuators. Here is a sample of a project. Listed here is only an excerpt out of Paparazzi-supported autopilot comparison table. As you can see, there are plenty to choose from. On the software side of things, the feature that even the simplest systems with a GPS support provide is position and altitude hold, sometimes also called loiter. For hovering vehicles, this feature is quite obvious. The aircraft stays on a spot at a designated altitude. In case of an airplane, this means flying circles around a set spot. A simple extension to that feature is homing. When powering on, the aircraft remembers the coordinates as its home position. During the flight, at any time, it is possible to flip a switch or press a button that will make the aircraft fly straight back to that spot. It is a great safety feature and an aircraft saver for beginners as well as experienced pilots. For follow me, an operator is carrying a GPS receiver. And the aircraft then follows the position of the GPS receiver like a virtual leash. I have the feeling this feature is not fully explored yet. I can imagine using such a feature to convert the aircraft into my personal cameraman. When flying an aircraft equipped with a gimbaled camera, it is possible to tell the autopilot to point the camera at a specific point on the ground. This feature is used very often by reporters and filmmakers. Waypoint navigation is, in my opinion, the minimal feature that needs to be provided before a project can claim that they support autonomous flight. This means you don't steer an aircraft yourself using a remote control. Instead, you mark GPS coordinates on a map, and the aircraft can navigate between those points. An extension of the waypoint navigation are survey pattern flights. In this case, the operator marks an area on the map and tells the aircraft to fly a pattern that will cover the whole area. That is very useful when you are generating maps, surveying crop fields, searching or studying tree canopies in the rainforest, for example. Almost all systems support some kind of geofencing. This means that if the aircraft leaves a virtually fenced-off area, it is able to perform some kind of an emergency maneuver. Depending on the regulations or mission requirements, it can then try to fly back home, switch off the engine and drop to the ground, or stay put and gain altitude instead of continuing the mission. There is a lot of more mission actions that almost all mature projects support by now, but these are mostly static flight plans. And the conditions change, and if the conditions change, one has to have connection to the aircraft to perform in-flight alterations to the mission plan. An improvement on that is using dynamic flight plans. One possible dynamic flight plan solution is implemented in the Paparazzi platform. The first-class citizen of a flight plan is not a waypoint, but a block. Each such block, consisting of multiple stages, represents an action. The actions can be setting system variables, altering waypoints, executing autopilot functions, or performing a jump to other blocks based on the system variables. These variables represent either sensors or counters. This solution represents a domain-specific language in which one can implement a dynamic flight plan. Each block is statically compiled croutine on the ground as part of the autopilot firmware. So the flight plan implementation is safe from accidental change in flight, but still can react based on conditions, providing flexibility without compromising code size, restrictions, and safety. A very similar system is implemented in the Gluon pilot too. Here I need to give them some props because they are saying on their website that it is exactly the way Paparazzi did it. The OpenPilot team is working on another solution that they are planning to release in the future. It uses a Python interpreter running on board the aircraft that can manipulate the waypoints and probably also the flight vector, but we will see how that works when that feature is documented and released to the public. There are many more things that we already can do, but this is how far we've gotten in the past 10 years. Now, let's try to predict a little bit into the future, or rather, let me tell you what I hope we will be working on next. Let us start with a great example of what is working very well so far. Paparazzi Sumo is, for example, that I have here on the stage with me. It's the aircraft here. It has been used for quite a while now by meteorological research groups as a reusable weather balloon. With basic training, the researchers that never flew an RC airplane before can take the Sumo, launch it, and gather humidity and temperature and wind information in air columns. Thanks to the efforts of the people like Martin Müller, it has become a standard tool that is as important as balloons themselves. Based on that, I believe we will see more drones used as sensor platforms. For that, I hope we will see more people like Martin Müller, who will make sure the solutions are standardized and deliver very repetitive results. On the other side of the spectrum, I was shocked to hear that a simple-seeming competition, the Outback Challenge, is still unclaimed. The mission consists of taking off from a runway, flying to a field that is 9.3 kilometers away, searching a 7.5 square kilometer area for a bright yellow dummy, and then dropping a half-liter bottle of water, it's a bit bigger than this, to the designated position. This sounds like a very simple job, but since the first competition in 2009, the main prize is still unclaimed. Teams were getting very, very close, but not close enough to claim the main prize. I have been told that the main reasons why teams fail is because the rules and requirements of the mission are overly demanding. So let's hope that the big prize will be claimed this year. But this has been made clear that the civil-use drones are still very much in their infancy. Drone technology, as well as the regulations regarding them, are in a need of advancement in order to mature. There is still a lot of pioneering work to be done. One striking development is miniaturization. There are plenty of very cheap and whatever quality toys in this area. But I believe this will be a starting point for an interesting burst of innovation, just like XUFO did during its time. There are already a few of the first really cool open source projects emerging. For example, Crazyflie by BitCraze. It comes with all the basic 10 degrees of measurement sensors and their own custom radio that you can connect to your laptop. The API is very well documented and the source code is released under open source license. This makes the device very compelling to anyone interested in experimenting with drones from the comfort of their chair. People are already doing very interesting things with it, like controlling it using Microsoft Kinect or adding sensors so it bounces off the walls without touching them, or adding their own 3D print and custom parts to the airframe. I think we will be seeing very cool stuff emerging based on this project. Other project that I'm closely involved in is the development of LISA-S in collaboration with the Technical University in Delft. The LISA-S is just the brain electronics, so just the pure autopilot of a UAV. I designed it to be as small as possible, making the size of a medium postage stamp, about 2 by 2 centimeters. It contains the 10 degrees of measurement sensors, a powerful ARM microcontroller with 0.5 megabyte of flash, as well as a GPS receiver module, while weighing only 2.5 grams. I have it here on the stage with me, so maybe it will be even smaller. Yeah. So, just like Crazyflie, I also developed a custom radio. The main reason was to save some more space and weight. The difference between SuperBit RF and Crazyflie solution is the compatibility with the Spectrum RC control system. This solution allows us to have telemetry with the laptop computer or tablet, and a standard model aircraft controller at the same time using only one module on the aircraft. Normally, these two channels are implemented using two separate radio systems. The initial motivation was an autopilot for a low-cost micro-helicopter airframes, as a retrofit solution providing additionally to the standard 10-DOM also a GPS receiver module, making it a perfect fully autonomous flights. And because it is just the pure brain part of the system, it makes it easy to mount on other airframe types too, like quadrocopters or airplanes, like these tiny things from China, for example. So you can just retrofit it with the board, and you should be able to fly autonomously with it. As I mentioned, we mounted a GPS on the LISA S, making it useful for outdoor applications. It is still not quite accurate as we would like. But thanks to companies like Swift Navigation, we will be getting sub-1000 RTK GPS systems that will provide a centimeter accuracy at 50 Hertz. This is quite an improvement from current GPS solutions that provide best case accuracy of 3 meters at 10 Hertz. This is a significant step forward for outdoor applications. For example, small separation swarms where you fly the aircraft really close to each other and you can draw things in air with them, for example. Or fully autonomous aerobatic flight, because this module also supports really high accelerations, what you have big problems with commercial modules. Or this is also a commercial module, but the modules that you can currently buy on the market. Or precision farming, mapping, and so on. But what about indoor applications? Sadly, indoor autonomous flight is still very, very challenging. There are some solutions available, mostly for research groups that with really, really deep pockets. For example, infrared camera tracking systems. These are the same systems used to capture the motion of actors for 3D movies, like Gollum from Hobbit, for example. They're great, very accurate and fast. Thanks to the solutions like this, groups like GRASP at Pennsylvania University and IDSC at ETH Zurich can create incredibly amazing demos. I bet you have seen their videos of swarm flight, snap-optimized flight planning, or ball-juggling quadricopters. The problem is that an infrared tracking system like this is very expensive. And because of this, out of reach are even the very rich hobbyists or less wealthy universities. Besides the cost, one has to dedicate a room for the micro UAV in order to mount the cameras in the room at very accurate positions. You can't just go with your drone anywhere and perform autonomous flight, so I'm throwing it out there. We need to work on some solution that we will have the following feature set. High accuracy, relatively cheap, no environment modification needed, light and very small, low energy and computational requirements. There are many approaches to solving this problem. Maybe laser-based radar, maybe computer vision, who knows? There are some very promising technologies on the horizon. One of them comes from a company called Technical Illusions. They are developing a new kind of virtual reality 3D glasses. The thing in the middle of the glasses is a tiny cell phone camera connected to an FPGA. They also will make a metallized gate array version of it to bring down the cost in pieces as well as need of power. It can track a blinking infrared LED pattern at 100 frames per second, providing a sub-millimeter accurate position and rotation of the user's head. I'm looking forward to mounting one of those on a nano drone. Another solution comes from TU Delft. It was released just a few days ago. It is a tiny stereoscopic vision module for their micro-flapping wing platform called Delphi. The system is based on the parallax effect of binocular vision, just like we humans and every animal with front-facing eye does. Using 2 cameras, this module can also see depth, not only a flat image. It is not a totally new concept. What is the size. As you can see, it is pretty small and thus light. It can detect obstacles, and according to MATLAB, it is also quite affordable. It enables Delphi to navigate autonomously. Definitely the videos look very promising. So here is like a time-lapse recording of the position of the aircraft, how it is flying in a room completely with no human control input. I think we are almost out of time, so let me leave you with a thought. In the world of PC software, we know about continuous integration, coding standards, static code tests, and so on. It is really hard to for embedded systems, and thus for all drone toys. I know many projects out there do software compilation tests and static code analysis on their software. But something I know we should work on is better reliability testing and for flight software we put on our toys. I know this will not happen overnight, but it is something we should make a priority of. I know this is not as much fun as flying them or developing new algorithms, but it would be a huge benefit, not only in this field, but other embedded system areas, to be able to do better regression and reliability testing. I know of the fact that there are some approaches provided as part of commercial development packages. What we need, though, are open source solutions for automated regression and unit testing tools for embedded systems. If anyone here would like to volunteer any solutions, that's why I'm telling you that, I would really love to hear from you. Thank you for your time, and I think we will be going to questions now, I guess.
As always, we have 4 mics, two there, just line up. Also, IRC and Twitter, we already have a question there. Go ahead, please.
Okay, so autonomous survey pattern flights are pretty useful for producing aerial photos, for example, for OpenStreetMaps, where you can draw a map based on these photos. Are there right now economically affordable solutions for that? And can you say something about the legal complications there?
Affordable solutions, the most affordable solution is definitely to build it yourself from some RC parts that you just buy off the shelf and then put an autopilot on it from any of those projects. Like Paparazzi in this case, you can buy the electronics and put them in. I'm pretty sure this is more affordable than buying an off-the-shelf, fully integrated solution. So basically, it's there. So this Sumo project, for example, is one of those that are built by a group of people that are using an open source platform for this. And there are other solutions, like I think Airdrone, the company, the Parrot, they bought something there. I don't know how affordable they are because I'm completely uninterested in buying anything from the shelf anyways, so I don't know. I rather build it myself anyways, and exactly suited the application. And it definitely is fully doable with the Paparazzi platform. And I'm pretty sure the others have some solutions for that too. The legal implications, this is difficult to say. It's like, I'm not a lawyer, and that's why I'm not talking about the legal stuff at all, because I know what I may do, where I may fly, and I'm happy that I grasped that. And getting into like, what are the regulations, you have to really look locally, where you are, what rights you have, who you have to talk to. It's like still everything in the infancy. As I said in the talk, we are still working on the regulation side of things, as everyone here might know. But it's like as a community from the open source side, we have to really, really push hard so that the regulations make sense, because what seems to be coming is really horrible. And but I'm speaking to the choir here, right?
Okay, thank you.
Number 3, please.
Yeah, I was also going to ask about the legal implications in regard to areas you may go to or altitudes you can fly. Maybe there's a certain space where you can fly under a certain altitude. Do you know at least where we can research that sort of stuff? What resources do you use to find out about that?
Yeah, well, it's like Google for it. But yeah, no, it's like there is here in Germany there is a club for RC airplane flyers. This is basically the rule set that you will apply to most of people that are trying to do this. The problem is exactly the regulation part of things is the problem that as soon as it is not a hobby anymore, there is not really any regulations available, and if they are available and people think that they know what the regulation should be, it is, no, you may not, and please don't compete with us big guys because we have the money. So basically that's what it ends up being. For the altitude part of things, it's, I think in Germany it's like 500 meters altitude maximum.
Above ground or?
Off the ground, so AGL, not full altitude. So if you are in the mountains above 500 meters, you still may fly 500 meters above the mountain. But this is only far away from an airport, as far as I know. If you are nearish an airport, you, I think, are restricted to 100 meters or something. But similar rules apply also in the US. It's like 400 feet maximum altitude. And if you are below 5, am I right, 5 kilos, then you may fly also outside of a designated field. Yeah. So.
Thanks. So we hope for Amazon lawyers to sort of things out for us, and we may fly to.
Yeah, that was a nice gag what they did there. Yeah.
Okay, thanks.
Number 4, please.
Hi. If I understood you correctly, you said you're only working on free software platforms, and I was wondering if you think about introducing non-military clauses to those licenses.
Well, if you add them, you are not open source anymore, right? Because you are excluding a group. So you may not discriminate anyone if you want to be really open source. So adding a non-military rule to it is against that rule. Thus, you are not really open source. So this is my take on this. And yes, I would love to block the military, but on the other hand, they have much better toys anyway, so it doesn't matter.
One more from the internet, please.
Okay, how secure are the solutions you presented for controlling a drone against attacks? So how easy is it to take control over a drone that my pal is controlling right now?
So this is what I mentioned also in the talk. It is a problem currently. It's like it's completely non-encrypted. It's like basically we are at this stage like the internet started out, practically is still. It's like all unencrypted stuff running everywhere around. It's like you run, like there was a great example from the Hack5 guys just again a few days ago. There was a great video where Darren Kitchen took like an aerodrone, and I think DJI, other quadrocopter, put a pineapple on it, flew to the aerodrone and overtook its Wi-Fi and controlled it from there. So it's obviously bad. We have to work on this now. But yeah, it's really necessary to do. It's like we need to secure this.
Okay, thank you.
Number 2, please.
Yeah. Commercial aircraft use a radio beacon system even today to navigate between waypoints over pretty much the entire globe, and this was done before GPS.
Yeah.
Since many institutions, buildings, etc., have a Wi-Fi network or some other industrial radio network, has there been any research done in using these like individual APs or individual radios for navigation? I'm thinking of like following a MAC address to a MAC address.
Yeah. So there were some efforts. I saw some universities mentioning that they were working on things like that. For a fact, it's like there was also recently some news that Apple is deploying like position tracking of iPhones to track their customers in their stores with quite high accuracy. So theoretically, that technology would be there to use Wi-Fi hotspots as basically radio beacons. I don't know of any go-to solution. That's the problem. It's like There are some DIY things here and there with a varying degree of accuracy and reliability and documentation. But it's like, I don't know, I think this is also one of the possible approaches, but I'm just looking forward to see if someone comes up with some really nice solution where it's like, oh, this works.
Yeah, because that seems like it could be a highly accurate, because these tend to be fixed position. You know, your IT networking staff are already going to know exactly where they are, so you should be able to construct a route.
Yeah, but they are being already used, for example, for augmenting your cell phone GPS position accuracy today. So, like Google and Apple, I think they are mapping also those. So, yeah, I'm looking forward to see something that is not a huge brick that I could put on one of my quadrocopters and test this. I'm curious to see that.
Thanks.
Internet.
Just a short one. Do you know about that challenge, about that Outback challenge? Are they allowed to refuel during the mission?
As far as I know, no. I think, yeah, there is something. You may come back after you scanned the field back home so that they can drop off pictures, so that you don't really need to solve everything, including the finding autonomously. So I bet you can refuel in that stage when you come back, but you still can't I don't think you can go to the field several times and refuel between passes. So you have to go there and scan the whole field in one go. I think this is what it is, but don't hold that to me. So.
Okay, thanks.
Mic 1, please.
What are the one or two main areas where commercial systems are more advanced than open source solutions? And why is it? Is it the time, the money, the smarts?
That's a difficult one. So yeah, definitely there are commercial systems that do some things better or different than the open source solutions. One thing is the obvious one that you have with a lot of open source projects in general. They are more tested, I think, or they are like basically they are not adding so much stuff so quickly so that the system is getting a little bit unstable at times. So they are like, okay, very conservatively, we add a feature, we test it truthfully, and then we consider maybe we should release it. At least some companies do, like not all of them. Like I know that 3D Robotics is releasing hardware that is like half tested, and then they have to do revision after revision, and not even, you don't know as a customer when you buy it that something changed, that the previous one was broken. But anyways, maybe they are doing some communication telling the customers, but this is what I heard. But then there are commercial companies that are like fully commercial and closed that really do also, it's more robust, I would say, the solution. This is from the feature set. From the feature set, there are more like the mechanical solutions. For example, I think there are some solutions to have like a hook on the wing, so you can land on a boat very easily. So you have a string hanging from a crane on the boat, and you can hook it in. But I'm pretty sure we could just build it also out on a CNC, cut apart, and do that to ourselves too. But I don't know of anyone trying that themselves. Otherwise, from the features, again, from the feature set, I don't know probably enough about the commercial systems to say what they really have. Maybe I should really actually do that and see what we need more to concentrate more in open source. But what we have to concentrate more is definitely reliability and repetitivity. Anyways, so basically things like this Sumo, that's why I showed Sumo, because this is Martin Müller with his guys really put the energy to make this thing fly every single time and work every time. This is like a rare thing in the whole open source world, where it's like, this is the solutions, this is how you build it, and you have a tool, like a hammer.
Internet.
How critical do you see the fact that the UAV challenge you mentioned is platinum sponsored by Northrop Grumman, which is a military corporation?
Yeah, so from the moral standpoint, I think it is crap, but from the other standpoints, they have too much money anyway, so we should take it.
Okay. So your point is still that the military already has better stuff and...
Well, they have better stuff that costs way too much money. This is why they're interested in our stuff, because it's much cheaper. And we choose solutions that they wouldn't even come up with because it doesn't have 50 certificates on it, basically.
Okay.
Mike 1.
Okay, I've heard there's a branch of science that investigates real animals like birds and flies, and to take inspiration from that to build machines.
Mm-hmm.
Does it play a role for your research?
Yeah, definitely. It's like, so the first quadrocopter ever was built by Ömische. It was before even the helicopter that we know today was even conceived. It was a quadrocopter, the first vertical takeoff vehicle at all, and he was inspired by dragonflies and their flight. So the propellers that he used on this were already back then inspired by birds. And definitely, the further you go, like for example, the Delphi, the flapping wing aircraft, of course it's biomimicry, right? So you are trying to copy the animals.
Okay, internet, go ahead.
What kind of sensors can we expect in the future apart from the current positioning, acceleration, and orientation sensors? Do you have any ideas on?
Oh, yeah. Which sensors? Additional sensors?
Yeah.
So yeah, that's basically the problem here. It's like we have everything to do autonomous flight very well outdoors. It's like on the airplanes you have one additional sensor is the pitot tube, so to get airspeed. So you can do control on that, but this is like also a normal part of the control system on an airplane. But on rotorcraft, it's like I think we have everything to do the autonomous flight by now, but what will come are other sensors that make it maybe more accurate. Altitude hold, like to keep the altitude more correct at ground level, there are ultrasound sensors being used. But it really also depends on the mission and the environment that you're running in. Down-facing cameras, just like Aerodrome does for optical flow. This is something they are using. The guys Pixhawk, ETH Zurich, they have an optical flow sensor that they are putting on their stuff. It's definitely coming too, but the minimum set, in my opinion, to do autonomous flight is the Tandem plus GPS solution. So, and then you have basically everything. You will get definitely other sensors depending on the mission and what you want to do. The indoor navigation, though, yes, the indoor navigation, there will be something will come. I really hope so. That's why I'm talking to you guys, because the smarts we have to put our heads all together because it's so interdisciplinary. This is also the thing here with the drones. It's like it's machining, it's electronics, it's software, it's aerodynamics, it's everything. It's like it's not a area where you can just concentrate only on your part, what you know about, and you won't be able to operate. You have to talk to so many people in many disciplines. And that's why I think, I really hope that someone will come up with really great solutions that no one thought about before because they are just thinking out of the box.
Okay, thanks.
Mike 1, please.
Okay, do you have an overview over the ROS integration, robot operation system in open source platforms?
Yeah, so ROS integration is ongoing. I know that, but there's some adapter for Mavlink, I think, for the ArduPilot stuff. Paparazzi has also some adapters for ROS. It has a converter from the IV bus that it is using on the ground station.
How good is this working?
As far as I know, it works. I didn't try it myself, so I can't tell you. But but this is not an open source platform. Aztec has, as a commercial platform, has a ROS integration. But yeah, this is something I would love to see, like someone who is actually really using ROS. It's like I used ROS in different research in the past myself. It's a great platform, so I would love to see it properly integrated with Paparazzi, for example. As far as I know, as I said, it has an adapter. People were using it. I don't know how well it works, though, because most of the missions and most of the stuff that is being done with this platform normally doesn't require to run with ROS additionally. It is definitely for multi-platform operation where you have to communicate with rovers and robots and humanoid robots. You would need that, yes, but I don't know of anyone who is involved in this project to be actually involved in this. You're welcome.
Thanks.
Mic 3, please.
When you're talking about regression tests, what do you really want to test, and where would you like to start?
So, as I'm mostly a low-level embedded person, it's like I would love to find a way. It's like I'm really thinking hard how to do it, but it's like I didn't come up with a reasonable solution. Is to be able to test the drivers on the lower level. It's like with the I/O and the hardware connected. This is really hard problem because you probably have to build some custom hardware to be able to run those tests with feedback loops and like switches and whatever. People are doing some things along those lines, but this is something I would start with because this is what I do. But other things is, on the very high level, there's some simulation stuff. This is an interesting thing. I know people are working on this. This will come. But it's basically that you have a simulation running. You basically take the newest revision from the code base, and you fly an autonomous flight plan in simulation. And if it deviates from certain parameters, then it will start screaming like something broke. And this is something completely the opposite side. And everything in between needs to be tested too. And so basically that's why I'm saying it's like, I know there are people that are software engineers that are like, oh, a drone, quadrocopter, I don't know. It's like, it's too much soldering and too stinky. But there are real software engineering problems in that area that we need the help of those people that are really have their head deep in software to solve this.
So you would like to decouple the sensors from the PCB and inject simulated
simulators or errors. It's like, yes, there is software in the loop. It already exists, but it is not an automated test system.
Okay.
That's what I mean. It's like, yes, you can do it on your laptop. You can run it in simulation, no problem. But it's like, how do you integrate it in a platform that runs on a server somewhere or a client and just goes through this every day when there are new commits?
Okay.
Internet, please.
Okay, what batteries have the best power density and are available to the public?
Ooh, that's like another hard one.
I mean, we don't need a manufacturer now, but just the technology maybe.
As far as I know, it is still lithium polymer, but I might be wrong that it changed by now. I know that LiFePO, or is the abbreviation, have the advantage that you can charge them faster, but I'm pretty sure they don't have the density of capacity. So I think lithium polymer is still the best, but tell me if I'm wrong.
Okay, thanks.
I would like to know myself if there is something better than this.
Last question, number 4, please.
For indoor navigation, would it be feasible to build something like a GPS but on ISM frequencies?
I bet it would, but it's my RF knowledge is not good enough. So building such a thing is over my capabilities, basically. And that's, yeah, I think it is a solution. I saw something, there is also a group that made a prototype. They built some antennas and on poles, put them in 4 corners of the room or 3 corners of the room, and then they had a receiver, and basically they measured the time of flight. You can do it much better where you measure the carrier phase, right? It's like then you have it much more accurate, just like you do it with GPS. So, but there is no, there are some very, very, very expensive commercial systems that simulate satellites indoors, so GPS satellites. I think this exists, but it is completely beyond any good or bad in price. This is like, this is not even the richer universities can afford that, I think. So yeah, but this is definitely a direction that would work nicely if someone would build a platform like that.
Okay, and we are out of time. Please once again thank Aston.
Thanks.